In this video, we're going to look at ways for visualizing the distribution of a single variable. In future videos, we'll also explore ways to visualize the distribution of multiple variables at the same time. Now, you may ask yourself, why do I care about visualizing or understanding the distribution of a variable? As we'll see later, a lot of the decisions we make in statistics about how we discuss or examine or interpret our data come down to the shape and characteristics of the frequency distribution. And while tables are awesome, sometimes a picture is worth 1,000 words, even if they can get a little geeky. Let's look at a few common ways of visualizing a frequency distribution for a single variable using different types of figures. Now, our choice of which figure to use often depends on the type of data that we're graphing. One of the most common ways to present data is with what's called a bar chart, also known as a bar graph. Bar charts are a way of illustrating the frequency distribution for a nominal categorical variable or for an ordinal variable. Here's an illustration of graduate student enrollment in the University of Maine in 2017 based on student major. Now, one of the first rules when creating any bar chart or similar figure is to always label your axes. Okay, not those axes, the axes of your bar chart. For example, here we have clearly indicated that our horizontal or x-axis identifies student majors. We don't need to guess what the groups are. It tells you that they're different majors. And we've also labeled our vertical or y-axis to indicate that it's the number of students in each major. Again, no need to guess what those numbers are. Maybe it's the number of course sections or instructors or something else. Nope, it's clearly telling us it's the number of students. On the bottom horizontal axis, we have 5 different majors indicating education, engineering, liberal arts and sciences, natural sciences, forestry and agriculture, and business. On the vertical axis, we have values indicating the number of students in each major. Now, each of the categories, in this case colleges, is then represented by a bar with the height of the bar indicating the number of graduate students enrolled in that major. Now, notice the boxes don't touch. That's because they're discretely different things. If the boxes touch, it implies a numerical sequential range of scores from low to high. That doesn't apply to nominal or categorical data, and it really doesn't apply to ordinal data as well. So you should use a bar chart or bar graph with ordinal data too. To see why, let's look at a different example. Consider student classification as well below, at or above state expectations in English and language arts. You could make a bar chart where our bars reflect a logical ordering from well below to above expectations. And we may initially see no problem with having the bars touch. After all, it does reflect a logical sequential ordering, doesn't it? However, in a bar chart, the width of the boxes are all the same. And if we make the boxes touch, this implies that the range of actual ELA skills is the same within each of those categories. But maybe the range of skills that fall in the meets category is fairly wide, but the range of skills that involve the partially meets category, maybe that's fairly narrow. And maybe the range of skills in the failing to meet or exceeding expectations is very large because there's all those skills in lower grades and all of those skills in the higher grades. So we have no way of thinking, are these all in fact the same with the same range of skills that you'd expect in each of those categories? It's similar to the issue that we saw with ordinal data when we were looking at runners who came in first and second in a race versus runners who came in second and third in a race. The difference between the runners who come in first and second may be very different than the difference in time between the runners who come in second and third. We know the order, but we don't know how wide each category is or how large the actual differences are between our groups. If the bars touch, it implies that the range of skills in each category is the same. So we should use a bar chart with ordinal data because the bars don't touch. Now, before moving on, just want to point out, you may also see bar charts where the bars are running left to right instead of up and down, and that's perfectly okay. Now, bar charts are a way of visualizing a frequency distribution for nominal categorical data or ordinal data. But what if you have interval or ratio data, data where the units are all equally sized? In that case, you can use a histogram. Now, histograms are similar to bar charts, except notice that the horizontal x-axis reflects clear numerical values, with the boxes indicating the number of cases within a given range of scores on some interval or ratio scale. Here's a histogram of chronic absentee rates in Maine schools. Now, absenteeism is an interval scale. In fact, it's a ratio scale, isn't it? Because it's a true continuum of equally sized units, the boxes in a histogram do touch, with those borders representing the exact lower and upper limits for each of the given ranges. You'll see histograms a lot because they're a very convenient way of quickly getting a sense of the nature of the distribution of scores. Is it evenly spread out? Are the scores clustered in the middle? Are they clustered at the ends? Or is it something else? But we'll get into that more in a later video. Now, a very different type of figure for graphing interval or ratio data is what's called a box plot. This example of a box plot is from a project I worked on in which we looked at gains in reading skills following an intervention that targeted struggling readers in first through third grade. The axis tells us that we're looking at a gain in reading skills as measured in grade level equivalent scores. 0.5 grade level gain reflects a child reading half a grade level higher when they finish the intervention. The box plot gets its name from, you guessed it, the box. The exact details may vary study to study or paper to paper, but you'll often see the box used to indicate the range of scores in a sample from the 25th percentile, or what's called the lower quartile, up to the 75th percentile, what's also called the upper quartile. In other words, half of the scores in the middle of our sample, the half of the scores that are in the middle of the sample, fall inside that box. You may also see the 50th percentile or median indicated with a line somewhere in the box. And you may also see the mean or average score indicated in some way, such as here it's marked with an X. Box plots will also indicate a vertical line that goes from the lowest score, typically ignoring extreme outliers, to the highest score, again, typically ignoring extreme outliers. For now, you can think of outliers as scores that really stand out as falling beyond the range of the rest of the data. For example, this score up here is an outlier. In future videos, we'll discuss ways in which outliers can give us a distorted picture of our data. Okay? So, as you can see, box plots provide a lot of information about the shape and distribution of our scores. Now, there is one more way of visualizing data that I want to discuss in this video. And while the box plot provides a lot of information in a concise, tight format, this other type of figure is kind of the exact opposite. And it's the infamous pie chart. Now, I'm sure you've seen plenty of pie charts in your life. People really do seem to like them, but not me. They're really a horrible way to convey information. In a pie chart, you divide a variable up into different categories, and then you carve up a circle or a pie so that the size of each slice corresponds to the percentage of cases in the sample that have each of those values. I think the perfect way to illustrate this is to make a pie chart based on national survey data of people's favorite pie. So we start with apple, which was the favorite for 14% of the people, and we keep carving up the circle based on the popularity of different types of pie. Ooh, pumpkin, my personal favorite, also apparently quite popular. But notice that it uses a lot of space and doesn't really convey much information. Worse yet, the information it does try to share, it does so rather poorly. All it tells you is how big groups are relative to each other. But how do you compare them in a figure like this? At best, it's extremely difficult to get a sense of the relative size of different categories. And to be honest, in many cases, it's hard to even figure out which slice of the pie corresponds to which category. The differences can be subtle to see. For example, this is a close approximation of a real pie chart I once saw in a paper I was reviewing. Now, note, because I was a reviewer, I can't show you the original, and I don't want to indicate the categories because I should respect the authors and the review process. But trust me, it looked just like that. I mean, how do you identify or interpret one group relative to another in something like that? As a result, many, if not most, experts on visual display of information are pretty critical of pie charts. They really do make horrible figures. They waste a lot of space and in the end communicate relatively little information. And the information they do try to convey is often hard to accurately evaluate. This is a better use of pi than using it to illustrate a frequency distribution. So these are some examples of ways of illustrating the frequency distribution of a variable. As noted earlier, there are a lot of other options too. And keep in mind, these are all pretty simple examples because they only focus on a single variable. Now, while we're focusing only on single variables at the moment, before wrapping up, let's take a look at a couple more elaborate visual displays that incorporate multiple variables. Here's another example from that project where we looked at an intervention targeting struggling first through third grade readers. This one just looks at first grade readers. Notice it includes several types of information. It tells you the student's grade level in reading at the start of the year, as well as their grade level in reading at the end of the year. It tells you if a student's score actually declined over the course of the year, or whether their reading skills showed some increase, but not as much as you would have expected during the time between the first and second test. It also shows you whether they've shown more of an increase in skills than you would have expected. These are the kids who are starting to catch up with their peers. And it tells you if they've actually caught up and are now reading at the expected grade level or higher. Finally, the size of the dots tell you how many students had a given combination of start and end of year test scores. A lot of information. Now, I wish I could take credit for this one. This is a figure illustrating Napoleon's invasion and withdrawal from Russia. It was created in 1869 by Charles Joseph Menard and is widely seen as the best statistical graph ever made. It's beautiful. It does a wonderful job of summarizing the number of Napoleon's troops, the distance they've traveled, the temperature, the latitude and longitude, their direction of travel into and out of Russia, and their relative location in correspondence to a specific date. I mean, it really is more than just a statistical graphic. It is a work of art. So, this is a good point to wrap up this video. In our next video, we'll take a look at some things not to do when making these types of visualizations and figures. Things you want to avoid and things you want to look out for when others do them. Okay? Bye for now.